Okay, now we'll go into the second part of the presentation. We're going to go into a little more detail on how a neuron actually works. This study, in terms of the electricity of a neuron, is called electrophysiology. Chapter 4 has some details on this. There's some pictures on 26 to 28 that might help you fill in some gaps. But basically what I want to do is kind of give you three little fun facts of the neuron before anything happens to it. The neuron is considered to be in a state of what we call dynamic equilibrium. And that basically means that the neuron is in its resting state, but there's a lot of things that are actually changing and going on during this resting state. It turns out that you have a lot more sodium outside the neuron. And sodium is positively charged ion, it's Na+. You have a lot more potassium on the inside of the neuron. And then if you look in your book, you can see they can actually measure the electricity. And it turns out before anything starts during this resting state, you basically have a negative 70 millivolt charge inside. So the inside is very negative to the outside. And basically keeping the sodium on the outside and the potassium on the inside and the negative charge, you basically got the sodium-potassium pump that kind of keeps this dynamic equilibrium going on. So I've got my little picture there, and you can look in your book about this some more. But that's basically kind of the basics of the neuron before you actually start a electrochemical signal. We call the electrochemical signal an action potential. This is the idea of generating an action potential and sending a neural impulse up to the brain. And so the idea is, in order to do this, and if you want to take some good notes on this, when you see something in the visual world or you hear something, that basically goes into your eye. And let's actually take a visual stimulus. It goes into the eye and it's changed via something called transduction into electrochemical energy. And in order to start an action potential, what basically needs to happen is electricity needs to be collected. Now if you look at that example of the dendrite from Roman numeral 2, basically in order to start an action potential, inside the neuron, we said the neuron starts at negative 70 millivolts. The neuron needs to collect from the dendrites 15 positive millivolts, 15 neurons of depolarization. If the neuron collects through the dendrites 15 millivolts of depolarization, then that will summate in the cell body and you'll get to negative 55, and that will start an action potential. Now, if you only collect 14 millivolts, nothing will happen. So this is considered an all or none type of phenomenon. So once you actually get this going on, a lot of very interesting things happen for the signal to be sent. So to start an action potential, you need to collect 15 millivolts of positive energy of depolarization. Once the action potential starts, you basically see the channels open up and there's basically a sodium influx. Sodium rushes in to the neuron. The channels actually open to sodium. There's selective, it's actually called selective permeability to sodium. And so sodium rushes into the neuron, turns the neuron actually positive, and then basically potassium rushes out, turns the neuron kind of negative, and then the sodium-potassium pump kind of recalibrates things. So that's what happens electrochemically during the start of an action potential. Now the other key thing that happens, and this all happens if you look at the neuron right at the start of the axon. It's a place called the axon hillock. It's right at the end of the cell body. But then the real important part of this is how does that electricity from the action potential get sent all the way down this axon? And it basically, this action potential is recreated in a point-to-point way as you go down the neuron. And so it's actually called saltatory conduction. Make sure you spell that right. I think I put it there. Saltatory conduction is basically the action potential is recreated at each one of these points. They're called nodes of Ranvier. So the signal is kind of sent down point to point. You wouldn't want to have the action potential going all the way down, but it's kind of recreated, making it going very, very fast. If you know the disease of multiple sclerosis, people's myelin sheath that kind of coats the nodes of Ranvier or the saltatory conduction are destroyed, and so it doesn't work properly. So we basically get to the end of the neuron. We got the electricity being communicated down there, and that's kind of the electrochemistry of the equation. I hope that makes some sense. The book should be able to add some details that you can add to this as well.